But that causes another problem, and that realization comes together with a problem. And frequently in science, what happens with one discovery is that it answers some questions, but it also introduces new questions. And that is fascinating. So why is the night sky dark? Okay, this is a really interesting problem to me because it's an observation that anybody could make, but the solution isn't quite as simple as it appears to be. So anybody would just tell me, obviously, because the sun isn't around. Okay, but like there's stars, there's galaxies that have hundreds of billions of suns in there. And so the night sky should have a lot of light too. And if the universe is infinite, then that means there's an infinity of other stars and galaxies that are sending their light towards here. And so surely the day and the nighttime should be equally bright. This problem is known as Olbers' paradox. Olbers was a philosopher that neither came up with the problem nor with the solution. I actually don't know why it's called Olbers' paradox, because he didn't really solve it or anything, but we remember his name for it anyway. So going back to this problem, if the universe is infinite, then there should be an infinite number of stars and galaxies sending their light towards us, making the night sky bright, right? But that's not true. Clearly, the night sky is not dark. I mean, it's not bright, right? So is the universe not infinite then? Because I guess that is against the idea that the universe was isotropic and homogeneous, which are proven now. So there must be some sort of assumption that I have made that was actually wrong, and I don't know which one it is. So let's think about that for a moment. Here's where Hubble comes back. So we have to reconcile these ideas that some of them are in conflict with other ones. So first of all, the universe appears to be homogeneous and isotropic. One more time. Homogeneous means that it's the same over here in this giant box of galaxies is the same as the next giant box of galaxies. Isotropic means that it looks the same in every direction. Even if that is true, then why do the galaxies move away from here? That's weird, right? Why are they moving away from here? What's so special about this place? I thought nothing was special about this place. Then the next problem is that the universe appears to be infinitely large, but there don't seem to be stars or galaxies that make the night sky bright. Instead, it's dark, right? So Hubble proposes the idea that the universe is expanding. And here, this is really important, expanding. I want you to imagine that you have a balloon, and on that balloon, you take a Sharpie and you make some dots, right? And then you blow up the balloon, and as the balloon gets bigger, if you had an ant standing on one of the dots, the ant would see all the other dots moving away from him, right? Or from it, right? And the ant would conclude that all the dots are moving away from them. But for every dot, every ant would see the same thing. It's not because they're moving away from each other, it's because the universe itself is becoming larger. The distances in between all the galaxies is becoming larger, and so all of them are receding away from each other. This is a solution that lets us have a universe that is homogeneous, isotropic, and the galaxies are all moving away without moving away from here. Remember, there's nothing special about here, right? The expanding universe. And the expanding universe is all very good. But I know that there's a question that tends to arise at this point. Now you want to ask me, what do you mean that the universe is expanding when you just said that the universe was infinite? And so if it's infinite, how can it be expanding? Then it would be bigger, right? What do you mean an infinity is getting bigger? I know that sounds weird, and I'm going to explain why that's actually not a contradiction. So here's the thing. Between the number 0 and the number 1, there are an infinity of numbers in between them, right? So for example, 0.5 is in between 0 and 1, right? 0.55, 0.555, 0.5555, all those numbers are in between 0 and 1. They keep getting bigger, but they can't be any bigger than 1, right? So there's an infinity of numbers in between 0 and 1. There's also an infinity of numbers in between 0 and 2. But there's more numbers in between 0 and 2 than between 0 and 1, but both are infinite. There's an infinity that's bigger than a different infinity, and an infinity that's smaller than a different infinity, while both are still infinite. And so the expansion of the universe is not in contradiction with the infinity of the universe. The universe can be infinite and still get bigger or smaller. Okay, so the speed of the expansion, how fast is the universe expanding. So Hubble was the first one to propose the expansion of the universe and also measure the expansion rate of the universe. His number was very, very far away from our current idea of what the number actually is, but that's not something to be taken against him. He did it best with what he had. So we think we have a really close measurement now that says that the universe is expanding with this rate that's measured by a value called the Hubble parameter, after Hubble, of course. And the units are a bit weird, so I'm going to stop for a second to explain what they mean. So it's measured in kilometers per second per megaparsec. So kilometers is a unit of distance and second is a time. So kilometers per second is a velocity, right? Kilometers per second, 1 kilometer per second is very fast. It's like a car moves at a speed of like kilometers per hour. So kilometers per second is very, very quick. A megaparsec is a unit of distance that's like 3 million light years pretty much. So what this velocity is saying, when this value says is 67.66 kilometers per second per megaparsec, that means that when you have two galaxies that are separated from each other by 1 megaparsec, so 3 million light years, they recede away from each other at a velocity of 67 kilometers per second. So if you think about how enormously large 1 megaparsec is, the expansion is actually seems to be very slow. In other words, the velocity that you would get if you're separated from each other, just the distance of the Milky Way, like 100 kiloparsec, 100,000 parsec, is really not much at all. It's a very small velocity. So the expansion actually appears to be very slow, but the universe is so immense, infinitely immense, that the very distant galaxies are actually moving very fast, right? So the expansion of the universe has been measured for a long time. Remember, the first measurement was by Hubble in 1929, right? And that number has been changing because Hubble got a number that was like 10 times too much, pretty much, right? The number has been changing, and now we have all these measurements from the year 2000 until today. Now we're actually coming to a point where the error bars are really small and the numbers are starting to not match with each other. So there's a discussion, there's a debate. The debate for the shape of the universe continues even today. And I'm not going to get into it now because it'll be discussed in a different talk later. But the point is that we are not done with this problem, okay?